Morning, guys. Yesterday we started looking at the beginnings of chapter 2. We started looking at the development of the atom. Remember, one big idea here is the atom itself has always been the atom. It's not like it has been transforming. It's just as we collect more experimental data, our understanding might have to shift so that it can make the predictions for the newer experiments that I do. We worked our way from the Dalton model, which was a solid sphere model. We took those notions, things are tiny, things are neutral. Thomson has discovered the plum pudding model, things that were actually tinier than the atom, electrons. Rutherford tested that model. So nice thing about science is it's always reproducible and testable against each other. And then we sort of worked our way towards the Bohr model. For the next two lessons here, we're going to specifically look at the nucleus itself. We're going to look at coming back to explain the question, how come on the periodic table, how come the masses sometimes actually have decimals? So for example, we're going to use chlorine in our lesson today. Chlorine is element number 17. It has an atomic mass of 35.45. The question here is, well, where did we get this 0.45 from? If a proton weighs about 1 and a neutron weighs about 1, how is it I actually have some decimals to the actual mass? Couldn't I have made it a little bit nicer? At first, you might be like, well, maybe it's the electrons. But electrons, like we said, is about 2,000 times tinier. You'd need to have a whole host of electrons for this to actually become decimals. Are we actually chopping protons and neutrons? We'll get that answer in today's lesson. Later on, after we sort of done all our nuclear chemistry here, radiation sort of studies, then we're going to focus on regular chemical reactions, look back at the Bohr model, see the experiments that he did to justify why there's different shells, and then come up with our last model electron configuration. So just for practice, towards the end of yesterday's class, I left you with just like a PhET kind of study. So those are subatomic particles. Let's just do this here for, let's have a chlorine. Let's have it as a chlorine 37. And let's do it once for a chlorine. Chlorine is a halogen, typically takes on a negative charge. Chemists are lazy, they don't typically go -1 or 1 minus there. So Cl minus, and I'm going to actually put a 35 here. All right. So let's have a look. Well, proton number is given by the element number. So in this case here, the element number, atomic number is 17. To be chlorine, both of these are supposed to be 17. No doubt about that. For the neutron number, however, we said, well, it's the particles in the nucleus, the protons and the neutrons together, that make up the total charge. If in this case here, if I filled in here the 17 later on, the number of protons, which I found, they sort of do it like that, so you can do the math here. 37 is my total mass, 17 are protons. If you subtract the two, well, this chlorine actually has 20 neutrons, whereas 35 minus 17, this one here only has 18 neutrons. So today we're going to introduce these two. The relationship that they have is they're actually going to be isotopes of each other. Isotopes here have different masses because they have different number of core particles, different number of neutrons. However, because neutrons are still neutral, it's not like they're charged because of the neutrons. So one has 20, one has 18. This is going to eventually come up and tell us how come there's decimals. And then in this case here, in terms of the charges, just assume things are neutral, right? We can see that, well, there's no charge in the corner here. If I have 17 positives, I better have 17 negatives. In this case here for electrons, because the chlorine has stolen an electron from someone, it now has one extra electron. It's been reduced. It now also has to have 18 electrons here. So you notice here I actually have one more negative than the positive, and therefore overall I am an anion. Hypothetically, I could have also had a negative charge. What if my electron number stayed at 17, and what if I dropped my proton number to 16? Well, that also means one extra negative. That would give me a negative charge. What's wrong with that, however, here is I'm not allowed to change the number of protons. The second I'm 16 for protons, protons makes me a different element. In this case, element 16 is sulfur. I would have gotten sulfur -1. So basically, in terms of charges, you can never change protons. You can only change electrons. The more electrons you have, it becomes anion, negatively charged. The more protons that you have, it becomes positively charged. Today's lesson here, I typed up for you here in the section on isotopes. I'll leave it in the sidebar with resources. I would say download it down, print it off, and then you can just scribble over it with me here. So let's make sure we understand what is an isotope and some of the terminology. How does this come back and explain why there's decimals? It says here for isotopes, most naturally occurring elements, take your pick of anything on the periodic table, most of them actually occur to us as a mix of what are called isotopes. Whenever we see this iso prefix, iso means something is the same. So they really like asking you this question here, define isotope. Tell me what's the same about them. In this case here, what's the same about them is they are exactly the same element. It's the proton number that makes you that element here, so it has exactly the same number of protons. However, even though there's something similar about them, they are isotopes here. They are different in some sense as well. What's different about them, I already showed you, is they actually have different masses. Well, if the mass basically comes from protons and neutrons, the proton number has to stay the same. What I'm really specifying is different is actually the number of neutrons. So in this case here, different atoms of the same element. However, they have different masses because of the neutron number. Those are the two things you want to mention. Most of our element samples here come as a mixture of isotopes. So just because I'm telling you chlorine doesn't mean every time I find a chlorine atom, doesn't mean every single chlorine actually has the same mass. I may have versions of it. In this case here, I have some versions that weigh 35. Some versions are a little bit lighter. Some versions are a little bit heavier. And because they're all chlorine, we know they all have to have the same number proton number. The only reason why they're heavier, like we just listed for you there, is because it has actually more neutrons. There's an important note here. Usually one is far more abundant. Even though these two forms exist, these two are isotopes to each other, it doesn't mean they're necessarily 50-50. In general, in nature, usually one of them is much more common than the other. That's actually going to come back on our periodic table. We're going to have to actually weight the average to represent the abundance. So, in terms of these isotopes here, because my reactivity is going to depend on my electrons, while isotopes will have the same number of electrons, isotopes are going to behave really similarly. That can be a good thing. Oh yeah, I don't care if I have the lighter version or the heavy version, it's going to behave the same. However, if I'm trying to separate these ones here, I can't separate it using a chemical technique because they're going to react in the same way. How can I separate them is I can leverage some of the physical characteristics as well. Anything that has to do with mass, so say, oh, they would actually have different densities because density depends on mass. Or diffusion or effusion rate here, half mv squared here. The particle speed here might actually be different. To separate them is a lot more challenging, but I need to go back to those physical characteristics. So just before we get into the math a little bit more here, they're giving you a little more practice with the PhET. So this time we're given hydrogen. If you want to know here for hydrogen on the periodic table, I'm given H, element number 1, and I'm given 1.01. What they're telling you here is, although hydrogen is a pure substance, although it is its own element, hydrogen actually comes to us in 3 different isotopes in 3 different forms. The most common form is hydrogen 1. What they've listed for you in the hyphen here, this one here is actually the mass number. So if hydrogen weighs 1, that's sort of like this one here. Well, to be hydrogen, I better be element number 1. So all these forms of hydrogen should have 1 proton. Well, how is it that I'm going to have different masses? Hydrogen is the one weird case that to weigh only a mass of 1, I already have a proton that weighs 1. Hydrogen actually has no neutrons. But what if a hydrogen wants to come back and show 2 or show 3? Well, then I have to have a different number of neutrons. We already said these are now isotopes of each other. You can give them other common names, protium, deuterium. Deuterium makes heavy water, tritium is radioactive. It's just based on different forms of the hydrogen. However, we said they're going to be the same sort of valence structure here. If I have 1 positive, I better have 1 negative for all these ones here to make sure everything stays neutral. So now imagine you were the first person doing this. You realize hydrogen in nature has these 3 forms. But you realize on your periodic table, there's only 1 spot for you on the periodic table. The question is, what would I do to actually represent this variation, this variety? Oh, I actually have some that are lighter, some that are heavier. Naturally, you might think about, oh, I want to take an average. How do we normally take an average? Well, let's take the 3 numbers. Let's go 1 plus 2 plus 3. I divided by 3 numbers. Okay, the average is 2. I should put 2 there. And yet when they've done the average, that is what they've done. They only have 1 number there. When they've done the average, I'm just going to sort of draw a picture for you. We have hydrogen weighing 1, hydrogen weighing 2, hydrogen weighing 3. So far, I'm going to call this one here the simple average. Averages like we know how to do here. Simple average puts us at 2, and yet you're going to notice their average, which has actually been weighted, their average actually leans much, much closer to 1. In fact, it's like 1.01. Right? So they are taking an average, but they're not doing it in the simple fashion that we're used to. So what they say here, masses on the periodic table here are not only averages, they are weighted based on their abundance. Just because you have these 3 forms of hydrogen doesn't mean that they're equally common. That's something your simple average assumes. If you have these 3 forms, 33% of them are the light type, 33% of the medium type, 33% of the heavy type, and that's why sure, on average is 2. But what if in my universe I have a lot more of the carbon number 1 than 2 or 3? Sure, my atomic mass may not be spot on carbon number 1, but definitely because I have the most abundant as hydrogen number 1, my weighted average needs to be skewed towards it. So I'm going to give you this formula here for weighted averages. You need to memorize this one. I'm going to say the average mass on the PhET, the periodic table, is a whole bunch of these combinations. Take the mass of the first isotope, but weighted by the abundance, plus the mass of the second isotope times the percent abundance. If you happen to have more than 2, you just keep tacking on a plus percent mass, plus percent mass, plus percent mass. Each of the masses that exist are weighted by their abundance, and each of them have a different say with the periodic table. We do average masses in other fields of science as well, so this is not necessarily specific to science, but this one here you want to memorize. I don't find it's that hard to memorize, but I'm just going to show you how the weighted average actually works out in this case. So let's try it out here for gallium. Gallium has 2 naturally occurring isotopes, so they say there's only 2 forms. They're actually giving us in our standard atomic notation, one form of gallium weighs 69, the other weighs 71. In terms of abundance, however, instead of being a 50-50 split, we said most elements occur, one of them is much more common than the other. Either the fractional abundance or the proportions, 60% of them are actually 69. The 69 should have a little bit more weight than the 71. So even as I'm just approximating here, I know the 69 is here, I know the 71 is here. If I did an even average, like a split, one plus the other divided by 2, that would put me straight at 70. Because I know the abundance is steadily higher for the lighter isotope here, I would expect my periodic table to give me an average mass that's slightly skewed towards the lighter isotope. That's the sort of proof with how do I know which one here is more common. But let's actually figure out what the periodic table did. So to put the weighted average on the periodic table, I'm going to take the mass of the first one. It doesn't matter the order. The first one is 69. Because I'm doing math with percent, I'm going to convert it to 0.600. I'm going to add this to 71 is the other type. I'm going to multiply it by 0.400. You multiply those two terms over. 69 times 0.6 plus 71 times 0.4. And this one gives us here 69.8. Again, it's best to say for an average mass on the periodic table, it's best to say no units, right? Because everything is relative to carbon just being 12. If you really had to, in chapter 1, we did gram per mole for molar mass, or you can use U for atomic mass units. That's how we weight the average. That's how the 69 type actually has a little bit more importance than the 71 in my average. One extra comment here is when we compare it with the simple average, for simple averages, we are used to adding things together. We're saying, what's the impact of this one or this one or this one? But then there's this notion of divide. How come in this one here, weighted average, I'm just adding numbers? Where'd the divide go? If you're really, really astute here, what we've done here, as I wrote the percentage as a decimal, this number here would have actually been 60 over 100, while this one would be 40 over 100. We have actually done the division part already in order to express these as decimals. Just before we come back to practice another question here, I'm going to pull over another simulation. All these simulations here you can find links to under the resources column. So let's just pull up a simulation. I'm going to show you for this simulation, we can actually play around with building different isotopes on the left side, so we're not going to use this too much. But let's say we have hydrogen, right? You can choose different elements here. It'll change it up for you. We have, well, to be hydrogen, I have to have 1 proton. I mentioned hydrogen is a little bit strange. It has the 1 proton. It actually has no neutrons. That's why when H becomes H+, if I happen to lose the electron on the outside, I really am just left with a single proton, and H+ is usually called a proton. We saw earlier a hydrogen 1 as an atom with the electron was called the protium. It's trying to tell you what the mass number is. I could, however, add in more neutrons. Well, I still have the 1 proton. That still makes me hydrogen, but now I have a total mass of 2. Now I'm in a heavier form. This was called deuterium. I can add on another neutron here. Turns out tritium is very unstable. That's what makes it not very abundant in our universe, but it can exist naturally, so I need to factor that into the abundance. You can play around with the symbol, sort of how I would lay it out. I have the element symbol, atomic number on the bottom left, mass number in the top left, and then also the abundance in nature here. If they tell me what it is, there's only trace amounts, means it's very little. And you can step your way through different elements here. They're not going to ask you guess what isotopes exist, but in giving you some information, oh, these are the 2 forms, these are the masses, they might ask you, well, what's the abundance? Or given, like the question, given our abundances, what's the mass I should put on the periodic table? What's more useful in the simulation here, if I either go back to the home or just click over here to the mixture. In this case here, sure, we have hydrogen 1, hydrogen 2. I actually do have the tritium form, but we said it's going to be really trace amounts. Imagine this black box here, this is everything in our universe. So far, there are no hydrogens in existence. What we can do with this simulation here is I can actually play around with actually putting the hydrogens into the universe. Let's say in the universe, I have hydrogen, and the only type of hydrogen is my lighter isotope. They're giving us a percentage composition. This is slightly different from what we did in Chapter 1. Chapter 1, we were saying, well, inside a compound, how much is mass for this element? In this case here, we're saying, out of the entire universe, how much is the hydrogen 1 form? Well, if all of it is hydrogen 1, 100% of it, the average mass here, you'll notice it's not quite 1. I mentioned to you a proton is a little bit over 1, but just for simplicity, it should be about 1. But there we go, it's 1. It's not actually any existence of hydrogen 2. What if I now put on a hydrogen 2 somewhere? Now my percentage in the universe is split. Now it's even. Half of them are the light type, half of them the heavy type. One of them weighs 1, one of them weighs 2. You notice what I would do with the simple average, it puts me roughly at 1.5. For my periodic table, however, to give me 1.01, that has to tell me I have way more of the light type than the heavier type. As I put this upwards, I now have this ratio for every 2 light types, I have 1 heavier type. And you'll notice that this, instead of being 1.51 or so, it's steadily skewed towards, in fact, my periodic table has at 1.01. I had to keep adding hydrogens. I want you to watch this arrow keep going downwards here. I want to keep putting it here. In fact, my universe looks something like this. I'm sort of putting all the hydrogens in our universe here. Even at that point, when 90% of them are the light type and 10% are the heavier type, I'm still not at 1.01. Keeping track that the purples are the lighter ones, the greens are the heavier ones, I can switch over to nature's mix, and nature here would look something like this. So hydrogen in our universe, yes, we do have the existence of some are light, some are heavy. But because the abundance is so much more for the light type, the average mass is skewed very heavily towards the light type. Instead of being roughly 1.5 what I would expect, it's skewed towards that direction there. Here's the percent abundance in our universe. So 99, almost 0.99% is the light type. We have the fraction, the trace amount, 0.01%. That's actually hydrogen 2. And again, you can come back and you actually take a look at multiple elements. Some of these ones here will have more than 2 isotopes here, and you can just add in each of the isotopes, watch what happens to the percent abundance, and how it has an impact on the average mass. Note the periodic table has already done all the work for you. The periodic table has already figured out what are the natural elements, what are the natural isotopes that they exist, figured out the percentages, and did the math that we just did in order to find that weighted average. Let's just switch up the math a little bit here. So going back to our OneNote here. Chlorine has a relative atomic mass of 35.45. So that's what the periodic table gives you. Right? So chlorine, 17, 35.45. We want to address this notion here. How come there's a decimal? So let's just do this with the question. Chlorine actually has 2 naturally occurring isotopes. One form is a 35, one form is a 37. So I want to know the percentage composition. I want you to tell me what abundant split would it need to be so that it can actually represent the 35.45. Let's just do a mental check for ourselves here. The chlorine 35 would weigh 35. Chlorine 37 weighs 37. A simple average would be add the numbers divided by 2. It put me at 36. Because in the weighted average from the periodic table, the weighted average is actually skewed towards the 35.45, we already are expecting the lighter type is more abundant. The lighter type actually has more say to the weighted average than the heavier form. So let's just try out our formula here. Our weighted average, I'm just going to say PT for periodic table, it's a bunch of these mass percent. All these terms here added up. Nicely for this question, we only have the 2 forms. I only need to tack on 2 of these numbers. Let's try it out here. For my periodic table to say 35.45, doesn't matter which one you label as number 1, 35, I can put 37, or you could put 37 first, doesn't really matter. But in this case here, it looks at first, wait, I don't have enough information. I don't know both of these percentages here, right? I should really say, well, this is X, and I want to say the other one is Y. But in this case here, if I have one equation, 2 unknowns, I can't solve it. Luckily, we're going to come back to this fact here. What if I told you these were the only 2 types of chlorine? If I told you 80% is this type here, more of it is this type, would you be able to get the other one? Well, sure. If 80% is here, 20% is there. What if I came back and said, oh, it's actually only 60% lighter type, the other one's 40%? How are you getting the other number? If these are the only 2 types, you know these 2 percentages have to add to 100. So what I'm going to do is I am going to set one to be X. The other one I want it to be 100% minus X. Again, I'm doing math here, so I'm going to put 100% as just a 1, and I'm going to minus X here. So I solved that issue. Because these are the only 2 forms, I can figure out how many is left over. and it really doesn't matter what you call x. You could have called x over here, you could have put 1 minus x. When you isolate and actually solve your way for x, whatever number is, you're still going to check back, what did I put x as a placeholder for? That's going to give you the mass of that particular isotope. So let me just work through this math here. Realize I didn't leave myself much room. I'm actually going to distribute this 37 in so that I can deal with the x. So 37 times 1 is 37 minus 37x. I'm going to sort of add up the x's, collect like terms. 35x minus 37x is negative 2x. On the other side, 35.45 minus off 37. Hopefully you find this math here is a lot simpler than what we did in chapter 1. Don't worry, in the math, in the algebra, it's come out negative. It only really sort of matters by the end of it. X as a percentage should be positive. What if I take negative 1.55 divided by 2? This now tells me x itself is 77.5. This is always a really nice hint. It may be a lot of work for you to isolate and solve your way for x. Do yourself a favor and back check. What was the question asking? What does x actually mean? Well, x is actually representing the percentage of the 35 isotope. So this 77.5, it's actually written as, 0.775 out of the calculator. This actually says 77.5% is the chlorine 35 form. The remainder, if I did 100 minus that, that would be 22.5%. This is 37 chlorine. So I should show you. In the calculator, it actually gives you to as 0.775. We know to convert that one there to 77.5%. So this last statement here is super important. You're going to notice in this question, you will never have a chlorine that actually has a mass, 35.45. You're never going to have a single atom. You put it on a scale. Oh, the periodic table says 35.45. Oh, that one there weighs 35.45. The only two forms of chlorine I have, you either weigh 35 or you either weigh 37. Fortunately for us, when we deal with reactions, we typically deal with a bulk sample. What they're saying is, if you give me a handful of chlorine, although no single atom itself will actually weigh 35.45, some of them will be the 35, some of them will be the 37. If I average them out, if I say, oh, over these 4 samples, I almost have a 3-to-1 kind of ratio here. So if I have a lot more of the 35 than 37, on average, if I take the handful of 4 atoms, on average, it's like every single atom weighs 35.45. I'm not saying the actual atom does, but I'm saying over the average, over those 4 atoms, it's like they all weigh 35.45. And if you think back to chapter 1, we've just been blindly using this one here as a molar mass that actually had taken into consideration, well, when you have a reaction involving chlorine, what if some of them are lighter? What if some of them are heavier? I've already taken the average. It's already taken these percentages into account. So which is why in chapter 1, we just use these directly as molar masses. We didn't even give it a second thought. Oh, is it actually the atom that actually weighs this? Well, no, it's none of the atoms actually weigh this fraction. I can't actually chop a proton or neutron, but what I actually have here is on average over a bulk sample, this is what it weighs. So let's just do a little bit more detail here. That is a formula you want to know. So this mass percent plus mass percent, that's a weighted average. That's what the periodic table gives you. Usually the question, however, is worded in the opposite way. Usually, well, I don't know, given some, I newly discovered an element. What are the isotopes that exist? What are the abundances? I don't know. I don't have it on the periodic table yet. I don't know the weighted average. Usually I run an experiment to somehow collect up the isotopes, to figure out what the percentages are, and then I put it on the periodic table. Nowadays in the new curriculum, all you need to know for this part is you need to know the name of the device that can do this measuring for you. The name of the device is called a mass spectrometer. If you go on to chemistry here, you're going to find there's different types of mass spectrometers. You can have a gas mass spec, you can have a liquid mass spec, whatnot. I'm going to roughly hint at how this mass spec actually does the separation for you. Again, it has to leverage a physical characteristic. But what this device does is it tells you what are the masses. So it tells you sort of what isotopes you have. And it also tells you those abundances. It tells you those fractional, in our universe, what percentage is this, what percentage is this. It actually gives you both so that we can then put it on the periodic table. In the old curriculum, we actually needed to know these steps here in more detail. For us, we're just going to take a quick scan over it. In next year, we're going to do a small section on spectroscopic techniques. We will revisit this mass spectrometer device anyways, so it doesn't hurt for you to know some of these characteristics. So the mass spec here is separated into 5 steps. I've listed the 5 steps so it only fit on the back side. I'll see if I can fit both of them together. We're going to start off with step number 1. Step number 1 occurs in the first part. Step number 1 is called vaporization. In some sense, this is just, let's vaporize them all into a gas state so that I can send gases through the rest of the device. It's a little bit hard to send chunks of solid or liquids here through a device. So what I'm going to do is I'm just going to atomize them, put them in the gas state. If I was analyzing, let's say, a sample of sodium, I would go sodium. Sodium starts off to me as a metal, it's a solid. I'd heat it up enough, so I'd atomize it into a gas. Great. That's that first step. At least it's a gas of the sodium metal here. Now it's ready to run through the rest of the device. What if they did chlorine, right? Chlorine was the one that we wanted to study. Some were the 35 form, some were the 37 form. Great. Chlorine as a nonmetal is already the gas type. But because this chlorine here, because this diatomic could be any number of combinations, it could be the 35 and 35. A diatomic here could be a 35 and a 37, or we could have a 37 and a 37. We actually need to break up this bond here so I can study each isotope by itself. Right? I don't want them to go through as a CO2. So even if your nonmetal as a halogen, weak London forces, it already is a gas, I still want to atomize them. I still want to separate them so they're individual particles. So that's what it means to atomize. We're going to produce a chlorine radical. It's going to be unstable, but it doesn't need to last for very long. Next step here is the most important. I'm going to then ionize it. What I'm going to do is I'm going to take a whole bunch of these chlorine radicals, right? Chlorine by itself here, I know it's unstable because it's unpaired electron. I'm going to engineer some car crashes. I'm going to actually send in fast-moving electrons. And all I'm trying to do is I'm trying to hit the chlorines really, really hard. As these electrons actually hit the chlorine, these first electrons just bounce off, ready to collide with other things. What I'm trying to do is I'm trying to dislodge electrons that the chlorine used to have. What would happen to the chlorine when it loses that electron? So if you did this here, chlorine had that unpaired electron. I send in an electron from the outside. This electron has nothing to do with the chlorine at first. This electron hits the chlorine. One of the electrons bounce off, so that's one of those electrons here. But since the chlorine itself, because the car crash was so hard, this electron actually gets removed as well. It's going to actually get ionized. Upon losing an electron, I then become a positive charge. Note this is a weird charge for chlorine to have. Chlorine normally when bonding is supposed to be Cl-. In this case here, I'm artificially causing things to become positive. In fact, if I don't fine-tune the energy and electron amount correctly, I might actually collide it with it too much. I might actually produce chlorine plus 2, plus 3, plus 5. That's going to become problematic later on. I'm going to try to produce just Cl+. Same thing I could do to sodium. If I bombarded them with electrons, engineer some fast-moving electrons, these electrons will just bounce off. I'm trying to dislodge electrons that sodium had itself so that it's positive. The whole goal is to ionize them, is to make them charged. The reason why I wanted to make them charged is step number 3. Step number 3, I'm going to accelerate them using electric field. Let's assume we've done that. We've put them into the gas state, we've bombarded them with these electrons, and suddenly I have a bunch of these Cl+. With these as Cl+, some of them will still be 35, some of them will still be 37. They're still not separated yet. Now that nicely they're charged, I can set up an electric field horizontally. So I'm going to put a relatively positive plate behind it, a relatively negative plate, and what I'm doing now is because it's charged, I can now control the deflection. I can now control the direction that they go. Because positive actually likes negative, the second that I start putting on this electric field, I can then start sending it through the rest of the device. So this case here is acceleration. That's based on an electric field. It's going to attract the cations here towards the negative plate here. For simplicity, let's imagine that there's just a single hole. Usually in real life, there's probably going to be multiple holes. There's a lot of chlorines that are not lined up with that hole here. They're just going to collide with the wall and just stay in the container until the really lucky ones are actually on a collision course with the hole. Then they can actually be accelerated. Not only can they be sped up, they can be sent to the rest of the device. This fourth step here is also important here. This is where the separation actually happens. This is called the deflection. We're going to actually couple it with a magnetic field. Notice that the magnetic field is oriented at 90 degrees. If you go into physics, you'll understand why that's the case. But in this case here, because they're also charged, because they're sort of zipping out of this pore here, the magnetic field will actually cause some deflection. At first, we're going to start off with no magnetic field. So all that's going to happen is when they went through the hole, they're just going to collide with this container here and never really make it very far. Then what I'm going to do is I'm going to slowly ramp up the magnetic field. So slowly make it a slightly stronger magnetic field. What's going to happen is some of those lighter particles are now going to be deflected, some of them are going to be bent because of the magnetic field, and some of them can actually make the turn, make the corner, and make it to the really end. Essentially, I have a detector at the really end, that's going to be step 5, that actually counts how many people make it at that setting. And all I'm going to do is I'm going to slowly ramp up the magnetic field. At first, my magnetic field was really weak. Only very light particles may have went all the way through. I slowly ramp up this magnetic field, slowly make it a little bit bigger. What's going to happen then is those light particles which used to make it, now they get deflected too much. Now they're going to hit the sort of the close side of the container. They're not going to make it to the detector. Some of those heavy particles, which didn't have enough deflection, because we now have a stronger magnetic field, let's say it's the chlorine-37 form, now it actually has enough deflection. Now it alone can actually make it through. So as long as I do a scan through of the magnetic frequencies, as long as I spend an even amount of time, I can get a relative proportion what masses are actually getting through at each magnetic setting. So I can figure out the masses, the isotopes themselves, that's where the separation occurs, and I can also get a count of how many actually hit at that time. We do want to keep this chamber here under high vacuum so that the particles don't accidentally just collide with other particles where they should have made it to the end and they actually don't. I keep that under high vacuum to make sure some of these can actually get all the way down to the detector. What we end up getting from this mass spectrum is from this mass spectrometer is called a mass spectrum. It's like a spread out of masses, and what it plots for you here is the percent abundance. It's how many relatively hit at that setting, and what I plotted against is the M per Z. The M per Z here is a mass per charge ratio, and here's why it was important here. If my charge was a +1, if I divide by 1, yeah, practically that's the mass of the isotope. So imagine here having no magnetic field, nothing hits. And all I do is I slowly ramp up the magnetic field. I hit no hits, no hits, no hits, no hits, no hits. By the time the magnetic field is strong enough for a mass 10 particle to hit, these ones here are now deflected enough, they collide, I just count how many reach me while it's on that setting. Then I set the magnetic field a little bit stronger here. As it's stronger, these particles here will now no longer hit. They're going to hit the walls of the container. Now the heavy particles which used to not hit, now they're going to hit. And in fact, if I spend the equal time on this one, I actually have way more hits on the 11 type. So now from the chart, I actually can realize boron in this element here, boron has a 10 form and boron has an 11 form. This is sort of a simplification here. It's not going to be a unique, it's just a straight line, exactly a 10. Usually it's going to be sort of, it took a while for the magnetic field to ramp up and ramp down, things like that. But what we're going to do is we're going to take the integral, we're going to take the area under the curve, the height or the area under the peak is proportional to how many particles are in that particular isotope. And this is actually where we get our atomic mass unit from. When we get that 10, that's 10 atomic mass units, 11 atomic mass units, relative to carbon being 12. I mentioned to you the relative unit 1 is very nice, but if you convert it back to SI units here, it's actually a very small negative number. Negative power. I mentioned before, from that bombardment state here, we try to fine-tune the electrons so it's divided by +1. It is possible. Let's go back to, in this case here, it's boron, so 10 and a +1. It's possible that the bombardment was so hard, let's say I have a fragment that's actually 20, and I actually dislodge 2 electrons. That's actually going to be problematic because if I do 20 over 2, that's going to behave like a +10 particle. So that also is going to hit, but that's actually not the same isotope. If I really had a 20 form and one that's a 10 form here, that's just going to confound the measurement. That's why it's really important for you to fine-tune the bombardment stage correctly so that we only have a +1, so that we have just the masses counted only once where it's supposed to be counted. So I'm going to leave you with these questions here. This is pretty self-explanatory. You're going to use the weighted average formula. This boron here also has only 2 types, mass percent, mass percent. It's just they're not writing out in words. So you can just say, well, boron is 10, boron is 11. They've given you the relative abundances. What if this was 19.9, the other was 80.1? It's relative. If I spent longer time at each of these masses, these peaks here would go higher, but at least relative by proportions, they'd be skewed up by the same ratio. So see if you can finish off that question. What is the weighted average? I already know based on the numbers, I have more of the heavier type. Between a mass of 10 and 11, the average mass should have been 10.5. Because I have more of the 11, I would expect the average mass should be leaning closer to 11, and you can match up with the periodic table what we get there. Magnesium, big difference. There's 3 isotopes here. Just add another percent mass term and see if it matches up with what you got on the periodic table. All right? So if you have any questions, just let me know. Thanks, guys.